Welcome to the video for slope fields, day 1. In this video we're going to learn about what slope fields are and explore how to see the connection between a differential equation and its corresponding slope field. So as a quick review, a differential equation is really any equation that is going to be using the derivative. So here we have a very simple differential equation. It could become more complicated, and it could even become more complicated yet. And a slope field is a graphical representation of this differential equation. So without further ado, let's jump into it. Okay, many times differential equations are neither separable or solvable by analytic methods. And we explored in the last section that we can use separation of variables to solve a differential equation. And that is what I mean by analytic methods. So approaching that, trying to solve for y equals. And they're not all solvable. So what we have is slope fields, and they're used as a way to kind of graphically solve a differential equation or give us a visual representation of what's going on with the differential equation. Now, it should be noted that the slope field is a general solution to a differential equation. If we were to plug in an initial value, that initial value will wind up drawing a continuous function through our slope field, and that would give us our particular solution to the slope field. So keep in mind that the slope field is just a general solution, and the curve which passes through after we have the initial value, we have the continuous function. So already hit on this, that a differential equation is an equation that uses the derivative. And basically what this means is the slope at any point, xy, is given by x squared. I've shown a example slope field that you might be familiar with. This is a weather map of wind, and we can see that when we're looking at this, we see the direction of wind at various points in the Middle East, in Iraq and Syria and Saudi Arabia. And if we were to maybe drop a feather right here in the middle of, that doesn't show up very well, right here in the middle of Saudi Arabia, we'd see that the wind pattern kind of pushes it and pulls it in a certain path. So these vector fields, or these arrows, point the direction that our feather might blow in the wind. And a differential field, a slope field, is basically a collection of all of these little direction arrows. Now, the direction is not important so much as just that a slope exists there. We're not going to get into whether this slope is going up or this slope is going down. So let's tackle this starting with example 1 on the next page. We'll draw our very first slope field, and then we'll do some matching of slope fields. Okay, so we are given the differential equation dy dx is equal to x squared, and that basically means that the slope at any given point xy is equal to x squared. So we can actually figure out what the slope is by evaluating it at certain points. So we'll go dy dx, and we're going to evaluate it at the point 0, 0. So we're looking for the slope right at this point, and if we plug 0, 0 into the equation, we get a slope of 0. So we can say right there at that point we have a flat slope of 0. And the slope field basically asks us to pick several points and plot all of the slopes. So incidentally, since there is no y in this equation, the slope will always be 0 when x is 0. So I could say plug in 0, 1 and get a slope of 0, 0, 2 and get a slope of 0, and all the way down several slopes of 0 right along that line there. If we take another point, we'll go dy dx. Maybe we want to evaluate it at 1 comma 2. So we plug 1 into the equation. There's no y, so we don't have any 2 to plug into it, and we get a slope of 1. And if we draw the slope there at 1 comma 2, this is a slope of 1, which is a 45-degree angled line. And again, this is a case where there is no y in our differential equation, so the y coordinate isn't going to change the fact that our slope is 1 all the way down. And finally, we'll do it for one more point. If we go dy dx, if we did it at, we'll say at the point -2 comma -1, that means for all x, we'll plug -2 into it, and for all y, we're going to plug -1, and we get an answer of 4. So 4 is a steep line, and, oops, I drew that at the wrong spot. -2 comma -1 is right there. And it looks, this line is steeper than the slope of 1. It doesn't have to be perfect, but relatively you want to make sure that you're going to show steeper than 1. If we go through and do that for all of our slopes, we find, again, the y-coordinate is unimportant in this differential equation. And going through and plotting all of our points, we wind up seeing the slope field fills itself out, and we have kind of a visual representation of the slope field, or the general equation to the differential equation, general solution to the differential equation. All right, typically when it comes to plotting these slope fields, because it's so time consuming to calculate the slope at every single point, people will rely on technology for doing that. On the AP test, when you're doing it, usually they'll only have you do it for 6 to 12 points, not that many points. But when we use technology, it can evaluate slopes at all sorts of locations. It doesn't have to be on integer values. We could evaluate slopes at 1 or maybe at 0.6 or 0.2. They exist all over, and we can kind of adjust the resolution of our slope calculations. And this slope field here is just a computer-generated slope field of the one we were doing above. We can see that instead of going at intervals of 1, it looks like they were doing intervals of maybe 0.25 or something to that effect. And we get a picture of what the general solution looks like. If we were given an initial condition of maybe 1 comma 1, we would plot a point there, and our curve passes through that point and kind of sticks with the flow of the slope field. So we might get a curve that looks something to that effect. And we could actually, this one, we could actually solve this differential equation using separation of variables. We'd get the integral of dy is the integral of x squared dx, and we find y is equal to x cubed over 3 plus c. And when we plug in our initial condition, we wind up finding that we get a curve that is a cubic curve that has been shifted upward. So this particular solution makes sense based on our separation of variables. But remember, we can't always separate the variables. So let's take a look at the next page. Okay, this is more in line with what you'd see on the AP test, a smaller graph. They place dots where they want you to calculate the slopes, and you shouldn't calculate it unless there's a dot there, because you're just spinning your wheels, going with extra time. But here we go. Let's tackle this. They give us the slope equation, dy dx is equal to x plus y, and we can start plugging values in there. And if I plug in 0, 0, I'm going to get a slope of 0. And if I plug in 0 comma 1, I'll get a slope of 1. If I plug in 0, 2, I'm going to get a slope of 2. If I plug in, let's go with, sorry, I was saying that wrong. 0, yeah, I said it wrong. 0, 0 is right here, and then 1, 0, and 2, 0. Had them backwards. If I plug in 1, 1, I'm going to get a slope of 2. And as we start to unfold this and plug in our slopes, we start to see sometimes a pattern emerges. And I encourage you to actually calculate all these out so that you can see that this pattern actually emerges. In this particular slope field, what we get is diagonals tend to have the same slope. So you can see that along this diagonal, we get a 0 slope. Along this diagonal, we get a -1 slope. This diagonal has a +1 slope. And that happens because you could do some analysis of this curve and be like, x equals -y, or you could say y equals -x. So I set the slope equal to 0, and so I'm going to see that, let's see, clean this up a bit. I'm going to see that if my slope is 0, then along the line y equals -x, I'll get all 0 slopes. And that's what we have going on here. And this is a really useful tool for when we go to find our equations given a slope field. We can kind of work backwards, and we'll be doing that in example 4. So part A asks us to find the particular solution given that initial condition. So if it passes through 0, 1, that would be this point here, and it would probably appear that that curve does something like this. And it's kind of hard to see because we don't have a lot of points plotted, but let's try another initial condition. We want to go with at the point -1.5, comma -0.5, so -1.5, -0.5, that would be about right here. Looks like the slope field kind of slopes in this direction. And then finally, with the initial condition, y of -1 equals 0, that would occur at this point, and our slope field would have us run right along that diagonal line. So the curves are our particular solutions given an initial condition. Alright, for example 3, I want you to take a shot at drawing the slope field. So go ahead and pause the video here, sketch in your slope field, and then we'll confirm against the results I have. Keep in mind there's no dots located along here, so we don't need to draw slopes there. So go ahead and pause it now. Alright, so it looks like we had a slope of 1 located at this point here and this point. We also had a slope of -1 on this diagonal, and then generally steeper slopes as we worked our way up. And again, they just kind of look at the relative slopes. The ones that are most important to get right are 0 slopes and 1 slopes and -1 slopes, and then the other ones should be relatively steeper. Part B says sketch the solution curve through 1, 1. So at 1, 1 we're at this point, and following this solution curve, pretty hard with the details that were given. Probably just kind of sweeps in like that. Okay, example 4 is really the most useful part of the lesson as far as how it relates to AP test, and it really kind of supports our understanding of slope fields and their relationship to differential equations. So let's talk about this one here. All right, so example 4 here, what we're going to do is we're matching our differential equations to the slope fields below. And what this consists of is kind of analyzing what's going on in the differential equation and looking for patterns in the slope field below. So in the first example, I see that I have 0 slopes when y is equal to 0 or 1. So what I need to do is find the differential equation or slope field that has 0 slopes at y equals 0 and 1. And looking through the list, it looks like right here we have 0 slopes at 1 and 0 slopes at 0. So this is the only one that I see that occurring on, so I'm going to say this is differential equation 1. Going back up to the list, on the second one, we have a 0 slope when y is 0, and our slope is undefined when x is 0. And another way to think of that is we have a vertical slope when x is 0. So we can go through and take a look at these things, and we see on one of these graphs slope of 0 when y is 0. Alright, here we go. Here's a slope where when y is 0, we have a slope of 0. And it looks like we have a vertical slope or an undefined slope when x is 0. Another thing that we can see is when y and x are the same value, we have a slope of 1. So this matches up with y over x. Okay, the next example, x times y. So in this case, we're going to get a slope of 0 when either x or y is equal to 0. So we're looking for flat spots along the axes, and not graph A, not graph B, not graph C or D. Looks like graph J. We have 0 slopes on this axis. We have 0 slopes on this axis. And even further on, we see that in the first quadrant, when x and y are positive, all of our slopes are positive. And similarly, in quadrant 3, when x and y are negative, all of our slopes are positive, because a negative times a negative is a positive. So this one is xy. Going up to the next equations. In equation number 4, what we see is when x is equal to 2, our slope is 0. So we want to look for 0 slopes along the line x equals 2. And looking at the graphs, these are not 0 slopes. These are not 0 slopes. It looks like option E has that 0 slopes going on when x is 2. We'll just check the other ones. That's a positive 1 slope. This is a almost 0 slope, but not quite. This is like a 1 slope. So yeah, looks like graph E, because we have those 0 slopes when x is 2. So this is the differential equation x minus 2. Going back to our formulas, the next one, this one here, graph number 5, or differential equation 5, looks like we'd have a 0 slope anytime x is equal to y. Our slope is 0. So we're going to look along the line y equals x and see if it's a 0 slope. And we see that actually in graph A. along the line y equals x. We have all these zero slopes that exist there. We could do some more analysis of it and try some sample points. If we have time, we can do that. But I think we've got it right there. Okay, next one. Sine of x. Well, we know sine of x is periodic, so we should be looking for a slope field that has periodic behavior. And graph B is not periodic. We have different things going on there. If we go to graph F looks periodic, but so does graph G. And graph F looks like if we were to draw something in there, we might have that. Graph G, if we were to draw something in there, we might have that. So we need some a little bit more analysis. Sine of x has a slope of 0 when x is 0. So we want a 0 slope on the line, and we see that occurring right here. Slope of 0 when x is 0. So this is our sine x, which probably means the other periodic one is g. Do we have any other periodic functions? Yep. Problem number 9 is periodic. Just to confirm, we'll talk about the slope on this one. We have a 0 slope when x is pi halves, or roughly 1.5-ish. And it looks like on G, when x is 1.5-ish, we have a 0 slope. So there we go. Here's our negative cosine of x. Okay. Looks like number 7, x plus y. We're going to have a 0 slope when y is equal to negative x. So we should look along the diagonal and right there. Oh, graph B. That one worked out nice. Along this diagonal, y is equal to negative x. We have a 0 slope. So this one matches with x plus y. In truth, I should check to see if that occurs on any of the other ones. It almost kind of occurs on this one, but it starts to get steeper down here. So, and this one's periodic. Do we have 3 periodic curves? Looks like we have 3 periodic graphs. This one, maybe this one's periodic. No, I don't think this one's periodic because we're not seeing any slope lines along the axes. We would probably see a slope there. So actually, if we're not seeing any slope lines, we probably have a vertical slope there when x equals 0, which means the function is undefined when x equals 0. And which one of these equations does that happen with? No, equation 8. When x is 0, the function is undefined, or the slope is undefined. So there we have it. Graph 8 lines up with number 8, I. So this is the natural log of the absolute value of x. We could do some further checking. Natural log of x is equal to 0 when x is 1. So we have 0 slopes when x is 1, or when x is negative 1. And we also have 0 slopes there. So that matches up well. Alright, so finally the last one. Looks like h is not there yet, and we look at the graph, or what's left. We have e to the x minus 2, and e to the x minus 2 will never equal 0, so we'll never have 0 slopes, but it when x is 2, the slope is going to be equal to 1, because e to the 0th is 1. So we should have a 1 slope when x is 2. And if we look at graph h, when x is 2, we do in fact have that slope of 1. So there we have it. H matches with e to the x minus 2. Okay, finally, in example 5, they give us some information in a slope field, and they want us to tell which of these is true. This says for all x less than 0, the solutions are decreasing. So we'll plot a point where x is less than 0, and here's a general solution, or a particular solution where x is less than 0. That's decreasing. But here's another spot where x is less than 0, and that function is increasing. So we know statement 1 is false. Statement 2, all solutions level off near the axis, and that seems to be true. If we take all of these curves, they all appear to be leveling off near the axis. So I'm going to say statement 2 is true. And then finally, part 3 says, for all y greater than 0, all solutions are increasing. So if we stick various points where y is equal to value greater than 0, we see that all of these particular solutions are increasing. So this one is also true. So we want the answers that 2 and 3 are true, and that happens to be only option D. Okay, I want to apologize. I know this video was a little bit longer. There's a lot of subtle details going on that's kind of hard to capture in words, so I needed to be a little more verbose than usual. Anyways, after this video, you should be able to draw a slope field given an equation. So if I said dy dx equals x over y, we would want to be able to draw the slope field for that. Generally, you'll only be given a few points to do the slope field at, so you'd want to plot only at those points. Okay, anyways, thanks for watching. Enjoy your evening.